Good morning, friends. In last lecture, we had seen the shear reinforcement in beam section. There are three types of uh, stirrups are used. That is inclined stirrups, vertical stirrups, and bent up bars. Now, there should be a grip between steel and concrete. So, there should be a bonding. So, we'll start with a bond. That is, it is a grip of reinforcement and concrete due to adhesion or bearing. Bond is due to combined effect of adhesion, friction and bearing. In concrete, it is very much essential that perfect bond must exist between concrete and steel to act both material as a unit. In concrete, the adhesion between concrete steel is provided by concrete during setting time. So next point is types of bond. See, here is first bond is anchorage bond. For transferring the force from the bar to surrounding concrete before it is terminated, the bond needs to develop is called as an anchorage bond. Then second one is flexural bond. It is change in the bar force along its length due to variation in bending moment in its length. And third one, development bond, that is the bond required to be developed for transferring the force to the bar from surrounding concrete. Then bond stress, the shear force per unit of nominal surface area of a reinforcing bar acting parallel to the interface between the bar and surrounding concrete is called as bond stress, or it is the intensity of adhesive force per unit of surface area. These are the values of bond stress for grade of concrete M15, the tau BD, that is bond stress. Design bond stress is 1, for M20 it is 1.2, for M25 it is 1.4 and so on. Now development length. The length of reinforcement embedded in concrete so that it can produce required stress by bond action is called as development length. See, the length of reinforcement embedded in concrete so that it can produce required stress by bond action is called as development length. It is also called as embedded length. The development length LD is given by, it is a very important formula, problem is asked here, LD 0.87 Fy into phi upon 4 tau BD, or phi 6s upon 4 tau BD, where LD development length, phi nominal diameter of bar, tau BD design bond stress. Factors affecting development length are grade of steel, concrete diameter of bar, grade of steel, concrete and diameter of bar. These are the factors acting on development length. And second one, design of bond stress. Then calculation of development length. Consider the development length for Fe415 sheet having diameter 12 mm, phi 12 mm, tau BD 1.92 for given grade of concrete, that is for M20, Fy 415 Newton per square. Then LD is 0.87 Fy phi upon 4 tau BD, that is 0.87 Fy 415 into 12 upon 4 into 1.92, that is 564.14 mm is the development length. So we'll say another problem. A 16 mm diameter bar of grade Fe500 is used for resisting compression. Calculate the development length if the design bond stress is 1.2 Newton per square, that is tau BD is given, for plain bars in torsion, that is LD 0.87 FYD upon 4 tau BD, that is 0.87 Fy 500 is given, D, this D is given as 500, the diameter of bar is given as 16 mm, see 16 mm, the depth Fy 500, the diameter of bar 60 mm, for tau BD 1.6, 1.25 is tau BD into 1.2, that is LD 725 mm. For tau BD, that is you have to consider the area, that bond stress is directly 1.2, this 1.2, and this is 1.6 into 1.25 is the is given in the formula, that is tau BD 1.6 into 1.8. See, this is the formula 120.25 into tau BD. Value of tau BD is increased by 60% and tau BD increased by 20% in compression. This is the given by IS code notification. Accordingly, we have taken that tau BD increased by 60% and tau BD increased by 20% in compression. This is in tension, 60% in tension and 20% compression. Now we'll see problem on design of shear reinforcement. This is the first problem. Design the shear reinforcement for a beam of size 250 mm into 400 mm effective. The span of beam is 4.25 mm effective, 4.25 meter effective. The beam is loaded with UDL 12.5 kN per meter including self weight. The beam is reinforced with 3 bars of 60 mm diameter bars of AP415. Grade of concrete is M20. We have to design the shear reinforcement. They are not given which type of shear, that is vertical, inclined or bent. So we'll start with the design. This is the given data from the problem. Then factor shear force you have to calculate, and factor shear force you load, that is WL by 2, that is W, because for a simply supported beam reaction is nothing, it is the shear force, and the reaction for that beam is half of this load, that is W into L if it upon 2, and it is shear force is 39.84, say 40 kilonewton. And AST 3 bars are given of 16 mm diameter, so AST is 603.18 mm square, and percentage of steel AST upon BD into 100, that is 0.60%. In step 1, calculate nominal shear stress, that tau V, that is VU upon BD. Just we have calculated the VU, that is 40 into 10 to 3 upon BD 250 into 400, that is 0.4 Newton per meter, that is the value of tau V. Then tau C max is 2.8 Newton per meter square for M20 concrete. So tau V is less than tau C max, hence it is okay. Then calculate tau C, that is shear strength of concrete, tau C. Percent of steel is given 0.60, so it is in between 0.50 and 0.75, and the value of tau C for 0.50% steel 0.48 and 0.75 0.56, but we have to calculate the value of tau C for 60%. So by interpolation you have to calculate the value of tau V for 60%, that is value of tau C is calculated as 0.512 Newton per mm square. So as tau V is less than tau C, shear reinforcement is not required, but provide minimum shear reinforcement in the form of nominal stirrups, that is 6 mm diameter bars of 2-legged with spacing. This is formula for spacing. Put all the values here and calculate the spacing of stirrups. So check for maximum spacing. This maximum spacing should not be less than greater than 0.75 D or 300 mm, that is 0.75 D, that is 300 mm, or SV should not be greater than 300 mm. Therefore provide 6 mm diameter bars, 2-legged vertical stirrups at spacing of 120 mm center to center. These are the stirrups, vertical stirrups provided at a spacing of 120 mm. This is a spacing of bars. This is a cross section of beam. So second problem we'll see. See here, tau C is given directly. A beam 230 mm into 440 mm effective is subject to working shear force. Shear force is also given. Working shear force is given. You have to convert it into factored shear force. Calculate spacing of 8 mm diameter bar, 2-legged stirrups. If percent of tensile steel is 0.75, take tau C. All these values are given. Only we have to design. So factored shear force you have to calculate 1.5 into 70, that is 105. Stirrups are given. Percent of steel is also given. Then we start with calculate nominal shear stress as tau V, VU upon BD, that is 1.014. Step 2, check for tau C max. Tau C max 2.5 Newton per meter square for M15. Since tau V is less than tau C max, it's okay. Calculate shear strength of concrete tau C, that tau C is given as 0.54 Newton per meter square. As tau V is greater than tau C, shear reinforcement is required. So to calculate this required shear reinforcement, you have to calculate the actual shear reinforcement required, that is Vs equal to U minus tau C media, assuming no bent up bars, that is 105 into 10 raised to the minus 0.54 to 13 to 40. That is for remaining shear force, you have to calculate the shear reinforcement required. That is for 49.11 kilonewton load, you have to calculate the shear reinforcement. For that, using 8 mm diameter bars of two-legged stirrups, the spacing is 332.59 mm. Checking for minimum reinforcement, that is minimum reinforcement is 394.5 mm. This is minimum spacing. Check for maximum spacing. The maximum spacing should not be greater than 300 mm or 450 mm. So spacing is 337.5 mm. So provide 8 mm two-legged vertical stirrup bars at spacing of 300 mm center to center. Okay, these are the types of problems.